Okay, so we're dealing with life history here, and I've given you the life history stage, the number of individuals, and the fecundity. So we're going to create a life history table and go from there for all of those summary parameters. So in the life history table, you're going to use what you've given and just keep going with it. So we have age, the number alive, the survival rate, the survivorship, the fecundity, the offspring per individual, and the age-weighted fecundity. And then when we use the short form, age is going to be x, the number alive is n sub x, survival rate is s sub x, survivorship is L sub x, fecundity is F sub x, offspring per individual is going to be a combination of Lx times Fx, and then age-weighted fecundity will be Lx times Fx times x. And I've asked you to do everything in years. So I'm just going to put years here down for x. We have 1, 2, 3, 5, 10, and 15. And then our number alive, 612, 610, 562, 470, 421, and 147. And then our survival rate will be based on nx plus 1 divided by nx. So in this first row, we're going to have 610 divided by 612, and that will give you 0.9977 if you're not rounding. And then for the next one, we do 562 divided by 610. We go on down like that. Remember for this last one that anything past 15 would be 0, so we're going to use 0 divided by 147, which gets us 0 for the very last one. And then for survivorship, that is n sub x divided by n naught. So every single time, whatever row you're in, you're going to divide by the original population size. So this would be 610 divided by 612, 562 divided by 612, and so on. For fx, those were given to you, so you can just copy those values over. 0, 0, 17, 19, 15, and 8. And now Lx times Fx. So this first row is 1 times 0. Our next row is 0.998 times 0. Then 0.92 times 17. 0.77 times 19, and so on. Alright, and then our age-weighted fecundity will be Lx times Fx times x, and we want that in years this time. So Lx 1, Fx 0, x 1, Lx 0.998 times 0 times 2, and carry that on down. Okay, so As you go through your calculations, remember what you're seeing here are calculations without rounding from a spreadsheet, but if you use a calculator, that's fine. I'll be able to figure out if you're rounding or not. So it's now time to figure out what our first summary statistic is. So R naught is going to be the sum of the entire column of LX FX. Okay, so when you add this all together, so when you add all of those values together of the offspring per capita, you get 42.49, and that is equal to RO. So that's one of the summary statistics that I asked you to calculate. 42.49. Alright, for G is going to be the sum of the LX FX times X divided by R naught. And so that's going to be equal to 3,942. Right, we're going to add this column up. So that was 3,942.7, and we're going to divide that by R, which we just solved for, 42.49, and that is equal to 92.78. So that's another summary statistic I asked you to calculate. So 92.78. And then the intrinsic growth rate, little r. Little r is equal to the natural log of R naught divided by G. Okay, so remember that the natural log is not the same as log, so the natural log of R naught is 3.74 divided by G, which we just solved for, is 92.78, and that is equal to 0.04. Okay. And then I also asked you for the optimum age at reproduction, and for that you're just looking for the largest age-weighted fecundity, and it looks like this age is the biggest, so the optimum age is 5 years old. And then finally, you've been asked to produce a survivorship curve. So for the survivorship curve, I'm just going to copy your survivorship, L sub x. Then we're going to adjust that so we can take the log. So we're going to take 1,000 times by L sub x, and then we'll take the log base 10 of that value. Alright, and we're going to need as well the age for all of these things. So those ages again were 1, 2, 3, 5, 10, and 15. And then our LX values were 1, 0.997, 0.918, 0.769, 0.69, and 0.24. and then we're just going to multiply those values by 1,000. So this one, 1 times 1,000 is 1,000. The next times 1,000 is 997.7, and go ahead and work all that way down. Alright, and then we need to take the log base 10 of what we just calculated. So log base 10 of 1,000 is 3. Log base 10 of 997 is 2.999, and carry on those calculations. Okay, so you finish your calculations and then you plot that to make your survivorship curve. And so on the x-axis, you're going to put age and years, and on the y-axis, you're going to put survivorship. Okay, so we're going to plot everything. So at 1, we have 3. And then at 2, we have 2.99. So that's basically right there next to it. And then at 3, we have 2.963. At 5, we have 2.886. And then at 10, we have 2.883. And then at 15, we've got 0. And then you construct your best fit line. And remember there's 3 possible patterns, type 1, type 2, and type 3. And I think that this looks like a type 1 curve. And then you just have to add everything that you need to support your argument about whether or not the population will persist.